Hello everybody. Today our topic is stellar remnants. As we saw last class, stars will spend most of their lives on the main sequence, fusing hydrogen into helium at their core. The energy released by these reactions counteracts gravity and keeps the star in hydrostatic equilibrium. When the star is on the main sequence, the pressure generated by the nuclear reactions at the core is enough to balance the gravitational contraction. But when the star runs out of hydrogen in the core, meaning that the core is now pure helium, fusion will stop, equilibrium is lost, and the core contracts, and the star moves off the main sequence. The core will contract under gravity while the outer layers of the star expand. As the core contracts, it heats up, and at some point the temperature and density become high enough for helium burning to occur, while hydrogen burning occurs in a shell surrounding the core. A small star like the Sun will fuse helium into carbon and oxygen but stop there. It's not mass enough to generate the temperature and densities necessary to keep going up the nuclear binding energy curve. A larger star will keep going, burning heavier and heavier elements, surrounded by shells burning lighter elements, arranged in a sequence of temperature and density. Even the most massive stars will not fuse elements heavier than iron and nickel in their cores, because they sit at the peak of the binding energy curve. Fusing iron with other nuclei does not release energy, rather it consumes it. Heavier elements than iron and nickel are mostly made inside supernova. Gold is made exclusively in supernova explosions. The dying stars, both low and high-mass stars, will cast off their outer layers. Low-mass stars will do so gently in a planetary nebula mass ejection. Like this one here. This is a picture of the famous Ring Nebula with the white dwarf at the center, surrounded by its outer shells that it's been blowing off. So for a low-mass star, you can see that this is the sequence of its evolution. It starts off as an interstellar cloud. That cloud collapses and forms a main sequence star. The main sequence star evolves into a red giant where it's burning helium at its core, and that then evolves into a planetary nebula and finally a white dwarf. Higher mass stars die much more spectacularly in what we call supernova explosions. Supernovas can outshine entire galaxies. There was a recent supernova in the galaxy M82, and here's the before and after shot. And you can see that once the supernova went off, it was actually brighter or as bright as the entire galaxy combined. And as we'll learn in future classes, galaxies of this size tend to have almost 200 billion stars in them. So in one moment, that star became as bright as 200 billion stars put together. Supernovas are so bright that they can be observed with your naked eye sometimes. The well-known Crab Nebula in the constellation of Taurus is a remnant of a supernova, and by studying this remnant and figuring out how fast it's expanding, we can actually sort of turn back time and see how long ago that supernova occurred. The number that astronomers come up with is 1054. So in 1054, a supernova went off. And in fact, that matches quite well certain records of, for example, Anasazi drawings in New Mexico, where there are records of people observing this supernova in daylight. So it's really very explosive events. So a high-mass star then starts as a big main sequence star, also evolves into a red giant, but then ends up its life as a type 2 supernova. And what's left behind, the core of the star, will become either a neutron star or a black hole, depending on how massive it is. So today we're going to talk about what's left behind. So stars eject their outer layers through either supernova or planetary nebulas, but the cores are left behind. And what happens to these collapsing cores? What's holding them up? Nuclear fusion has ended, and so there's no energy coming from nuclear fusion rates to counteract the effects of gravity. What happens to the cores of these dead stars is going to depend on the mass of the leftover core. The important mass to take into account now is the mass of the core, not the mass of the original main sequence star, because really all that's left over is the core of the star. And so, depending on the mass of the core, you might get a white dwarf, a neutron star, or a black hole, in increasing order of mass. White dwarfs and neutron stars, as we'll see, are held up by degenerate pressure, and degenerate matter behaves very strangely. We'll also learn that nothing can stop the collapse of a black hole. We'll see that when neutron stars are rapidly rotating, they can cause pulsars, rapidly changing stars with rapidly changing brightness, periodic rapidly changing brightness. We'll also learn that even though black holes are invisible, since light cannot escape them, their effect on the surrounding material is not, and in fact we've detected many stellar mass black holes in our own galaxy. So, in all of this discussion, the important thing is always the fight, the struggle between gravity trying to push stars in and pressure pushing them out. In a spherical collection of matter, no matter how big or small, will always want to collapse under its own gravity. The bigger and denser the object is, the stronger the gravitational attraction will be, so the more the object is going to contract unless another force steps in to counteract gravity. So if that's the case, then why doesn't the Earth contract? Well, it does, a little bit. The temperature and pressure inside the Earth will go up quickly as you travel to the core, and they become high enough to melt iron. What holds the Earth up from further compression is just simple electrostatic pressure, the fact that atoms in liquids and solids resist compression, because they don't like to be very close to each other. Their charges repel one another. This force is not very strong, so it can only hold small amounts of solid matter apart. Small amounts, I mean, like you and me and the Earth. But once you increase the mass and density of the object, say to the size of a star, you're going to need a stronger force to counteract gravity. For most of the star's lifetime, nuclear fusion provides the pressure necessary to keep gravitational collapse at bay. Once nuclear fusion reactions can no longer occur, either because in low-mass stars the temperature and density aren't high enough to keep fusing heavier elements, or in massive stars you've reached iron in the core, and that can no longer be fused energetically in an energetically favorable way. Then the stellar core is going to need a different source of pressure to keep it from collapsing. The type of pressure that holds the core up is going to depend on how massive that core was to begin with, because the higher the mass, the higher the gravitational attraction, so the stronger the new force must be. When stellar cores have masses less than 1.4 solar masses, they collapse until they form white dwarfs. In a white dwarf, the mass of the Sun is compressed into a sphere that's about as big as the Earth. The density of a white dwarf is 1,000,000 times larger than that of water. And if you took a piece of white dwarf as big as a sugar cube, you would actually have the mass, it's equivalent to the mass of an entire car. At these densities, atoms are shoved so closely together that the electron orbits start overlapping with each other. Electrons don't want to be near each other, and they will exert pressure in order to not occupy the same energy levels. We call this state of matter degenerate, and the force exerted by the electrons is called electron degeneracy pressure. Degenerate matter behaves really strangely. For regular matter, like you and me and the Earth, the more mass an object has, the bigger it is. For regular stars on the main sequence, the same is true. The more massive they are, the further up they are on the main sequence, and the bigger their radius will be. For degenerate matter, the opposite is true. The more massive the star is, the smaller it will be. That's because the more massive the object is, the stronger the compression from gravity. But the repulsion between the electrons doesn't really increase in step, so that a 1.4 solar mass white dwarf is actually smaller in size than a 0.5 solar mass white dwarf. For regular stars, if you increase their mass, you increase their size. For degenerate stars, if you increase their mass, their size actually decreases, which is really counterintuitive. For stars that are larger than 1.4 solar masses, gravity will be even higher, and the electron degeneracy pressure is just not strong enough to keep gravity at bay. That means the star collapses further and becomes denser and denser until a new force steps in. This time, that force is neutron degeneracy. Neutrons being too close to each other will repel each other very strongly, and a neutron star is formed. This is an image of a neutron star in the middle of a supernova remnant. For stellar cores with masses greater than 1.4 solar mass, but less than 3, these stellar cores collapse until they form neutron stars. For a neutron star that's up to 3 times the mass of the Sun, you compress that into a sphere that's only as big as Tucson. The density of a neutron star is 2 times 10 to the 14 times larger than water. And how much mass would be in a sugar cube of neutron star material? Well, as much as the entire humanity, all of humanity. So 7 billion people could fit into the space the size of a sugar cube. Neutron stars are extremely hot because they're so dense. The temperature of this star, observed by the Hubble Space Telescope, is 660,000 degrees Kelvin. However, they're still extremely challenging to observe because even though their temperature is extremely high, their radius is tiny. The radius of this neutron star has been measured to be less than 27 kilometers wide. So you know now that even though the temperature is very high, the surface area is very low, and so the luminosity will be low as well. It's actually an extremely faint object, requiring a telescope in space to actually see it. The other exciting thing about neutron stars is that they rotate extremely quickly. This is a consequence, if you think about it again, of angular momentum conservation. The core of the star starts off large and collapses under gravity, and as things collapse, their size decreases and they spin up. So any rotation that they had initially just gets amplified by the stellar collapse. So as it spins up, it starts rotating faster and faster. Neutron stars also have very strong magnetic fields, and they emit beams of light. These beams sweep the sky because the magnetic field and the rotation axis aren't always well aligned. And you can see that in this diagram here, where you see the magnetic axis along which the light is beamed is actually offset from the rotational axis. So if you imagine this thing rotating, you'll see this beam just sort of scanning the sky. This is called the lighthouse model for pulsars, for obvious reasons, I guess. Pulsars were first discovered by Jocelyn Bell in 1967. Here's an image of a pulsar with a period of 1.3373 seconds. The amazing thing for Jocelyn when she first discovered these was how regular these pulsations were. They happened, they always, the time lag between each pulse was extremely accurate and always the same. And that led her to call the first object that she discovered like this, LGM, that stands for Little Green Men. She was convinced that an object that put out pulses with such regularity had to be something made by intelligent life. What she found was something almost cooler than that, the fact that you have a star that's rotating so fast that the entire star, taking up 27 kilometers in radius, can rotate in 1 second. I mean, that's a pretty incredible thing to think about. And the reason why these stars can spin so fast and not blow themselves apart is that the gravity on them is just so strong because they're so dense. They can really keep together even as they're going through this intense rotation. And for any Joy Division fans out there, you might see this is the cover of one of their albums that shows the pulses from this first pulsar discovered. The Crab Nebula is a supernova remnant in the constellation Taurus, one of the most famous, again corresponding to the supernova that went off in 1054. Crab Nebula, the Crab Nebula has a neutron star at its core, and that neutron star spins 30 times per second. So it rotates on its axis 30 times in 1 second. So what happens now if the mass of the core is greater than 3 solar masses? When the mass increases, again the gravitational attraction also increases, and that means the neutron degeneracy is no longer strong enough to hold the star apart. And in fact, nothing is. The star will collapse all the way down to a point mass, an infinitely small and dense black hole. Black holes don't have a surface, but we still talk about their sizes. For example, one might say a black hole with the mass of the Sun would be only 3 kilometers wide, about the size of downtown Tucson. But what does this mean? Black holes don't have a surface, but they have an event horizon. The event horizon is defined as the boundary beyond which not even light, at its speedy 300,000 kilometers per second, can escape. Beyond that horizon, the black hole is black. No light is emitted from that region. So here's a picture of a black hole. If no light can escape black holes, then how can we detect them? How do we know they exist? Aren't they just a theorist's dream? Black holes themselves are invisible, but they have a lot of influence on nearby objects. As you approach a black hole, the gravitational force will increase drastically. We detect black holes indirectly by observing stars orbiting around empty space under the influence of some invisible mass. So if we were to observe the star as an astronomer and we see that it's orbiting around what looks like empty space, but we know that, as Newton told us, that force equals mass times acceleration. So again, if this star is moving in a circular motion, that means that its velocity is constantly changing, which means that it's accelerating constantly. And where there's acceleration, there must be a force. That force is gravity, and it's the force of gravity between this star and an invisible black hole at the center. Sometimes we can observe black holes a little more directly, because sometimes stars orbiting those black holes get a little bit too close. And what happens then is that some of the material in the outskirts of this big star gets pulled into the black hole and starts orbiting around the black hole in an accretion disk, so in a disk surrounding that black hole where the material gets accelerated to such high velocities and temperatures that it actually starts emitting X-rays, and we can detect these things by pointing X-ray telescopes at them. This is an artist's impression, of course, but this is what we believe happens in these things. So you have a star, that star feels the attraction towards the black hole, and some of the material sort of funnels into it through an accretion disk. and as the material gets accelerated towards the black hole, it starts emitting X-rays. So remember back to this question we were asked in class. If the Sun were suddenly replaced by a black hole of the same mass, the Earth would A. remain in the same orbit, B. move into a smaller orbit, or C. move off the current orbit in a straight line, or D. be pulled into the black hole. As we discussed in class, black holes are not cosmic hoovers sucking up everything in their pathway. They just attract things following, Newton's universal law of gravitation. So if you replace the Sun with a black hole of the same mass, then nothing changes. The attraction on the Earth is going to be exactly the same at the Earth's distance. So what makes black holes so powerful, and why are they, why do they really capture Hollywood's imagination? The question here is that even though the mass is the same, it's been concentrated in a much smaller radius, which means that you can get a lot closer to the black hole, and so d in this equation is going to be a lot smaller. As d decreases, the force is going to increase, and it's going to increase as the second power because it's d squared. So as you get closer to the black hole, the force gets much, much stronger. That means that even though black holes are not cosmic hoovers, things do get a little bit weird when you get too close, because gravity becomes so strong because of that factor of 1 over d squared. And this movie here shows you what it would look like when you approached a black hole from a distance of 100 times the event horizon to 10 times the event horizon, and you'll see it goes by a little bit fast, but you'll see that the stars surrounding that black hole seem to be, the light from them seems to be bent away from the location of the black hole. And we're going to talk about this bending of light, which is actually a natural consequence of general relativity called gravitational lensing, a little bit later in the course. So as a summary, what happens to the cores of dead stars is going to depend on the mass of the leftover core. If you have less than 1.4 solar masses, you get a white dwarf, held apart by electron degenerate pressure. If you have a mass between 1.4 and 3 solar masses, you get a neutron star. These are held apart by neutron degenerate pressure. Stellar cores that are more massive than 3 solar masses end up forming a black hole because there are no forces that can keep such a dense distribution of matter from collapsing upon itself. Degenerate matter behaves very strangely. The more massive a degenerate star is, the smaller it's going to be. We also learned that pulsars are rapidly rotating neutron stars. And we learned that black holes are invisible, since light cannot escape them, but that their effect on the surrounding material is not.